Good morning, everybody. I hope your 3-day weekend was nice. Good. I have made up my typical roll sheet here, right? You saw this very briefly last semester, so I'm just going to pass it out and you can check off the boxes, right? So if you would, please fill out last week. And then start filling out this week. No fair going, into the future unless you are a Time Lord, in which case we have to talk about your growth time. But what you want to look, this is mostly so that you know that you're like registered, right? If you don't see your name on this sheet, there's a very big problem. So just a check mark. You don't need to do your initials or sign in blood or any of that kind of stuff, right? But please fill out last week's and today. There was an issue in Canvas that was affecting your homework, and people emailed me, and I'm grateful they did, because for some reason, Wiley Plus reverted back to its default setting of expecting sig figs in your homework.
It did, yeah.
It's like possessed. I don't. So I went in, and I again changed it back to don't do that, and hit save. And I checked again, and it was still there. So hopefully now it's working. Please just let me know if you think it's still working. Again, always assume that you are right and it is wrong. That's the basic of it. For those of you that bought a year's code last January, there were 9 of you, and I have sent messages to you with codes, right? So if you feel like you were left out, you need to let me know also. Homework for chapter 15 is due this Saturday? 15 and 16 at the same time, right? So we got a lot to do today. Good times. We were here, okay? And just to sort of refresh you from 3 days ago, or no, more than 3 days ago, we were looking at a pendulum and trying to turn it into a spring, right? We're trying to apply this very powerful toolbox that we have for simple harmonic motion. And today, we'll finish this up. We're going to talk about what happens when you put friction in simple harmonic motion. And then we're going to start applying the principles of simple harmonic motion to waves. That's sort of the story arc for today. And we'll be here hopefully about an hour, 15 minutes, hour and a half, something like that. And then I'll give you time to do your homework. All right. So we had taken this simple pendulum, and I was in the process, of massaging this into something that looks like a spring. And I started pulling some dirty physics tricks here. Now, some of the engineers hear our siren call in physics, and we sing to them that, you don't have to worry about stuff, and just come over to our side, come to the dark side, we have cookies, right? Like it's this small angle approximation becomes very powerful for simplifying your life in a lot of different ways. When you don't do this approximation, you get nasty differential equations. What we're trying to do is avoid solving a differential equation altogether, even though we've got one sitting right here, right? Like this is a second order differential equation with thetas and s's and all kinds of stuff. So kind of the big, not aha, but the part that you might be, very new, uncomfortable with in terms of mathematics is, look, I've got a differential equation that's got length on one side, okay, like an arc length, okay, this S is arc length. And I've got an angle theta on the other, right? How do we solve that? Well, we don't. We cheat, okay, by using the small angle approximation. By cheat, I mean we're using numerical approximation, really. And how small does the angle need to be? Yeah, for engineers, nothing more than 5 degrees. Okay, for physicists. All right, so we're at this point, and we're trying to make it look like this equation up here. That's the pattern we're trying to follow. And we're getting there. It's just we have thetas and s's and all kinds of stuff. So we got one more substitution to make. And that's the arc length substitution. What's the arc length in terms of the angle? Yeah, it's the radius times the whatever amount the angle is in radians. So our radius here is the length of our pendulum. And so we can compute the arc, right, that this thing swings through. We can find that whatever arc length that is in terms of theta. So that lets us write L theta in here, dt squared, right, minus G, G, not Q, G theta. All right, so I'm going to just divide both sides by L. So we got minus G over L right there. And now I have an equation that is the second derivative with respect to time of our function, of our variable theta, equals some constant times that same thing. And if we look up here at the green, we have this same pattern right here. We have a second derivative with respect to time of a function x, and it's equal to some constant times x. So now, these two equations in the blue boxes, they match. Functionally, they are the same thing. In fact, if I just swapped theta for x as a symbol, and I swapped G over L for omega squared, I'd be done, wouldn't I? This is semantics now. But physically, what we do is we go, oh, well, if that's the case, if I've got the same pattern, and the one in green is already solved, I have a full toolbox for this equation that's over here in green. What do we do to unlock the toolbox? We find omega. Well, we've just found omega. What's omega squared? Not negative. The negative is the same. Got a negative there, got a negative there. So what's omega squared? It's just G over L. So in doing that, okay, we pattern match. We go, oh, well, omega is equal to G over L. Again, we're coming from, right, looking at this equation, seeing that it's functionally the same. Second derivative, negative sign, some constant sitting in front of function. Well, there's some constant sitting in front of function. So the thing that acts like omega in the pendulum is the square root of G over L. And now that we have omega, we can find everything else out. We have now unlocked the toolbox, and the full toolbox comes to bear, such as the period of a pendulum. This is kind of like our whole reason we wanted to get there, okay, was to figure out how long it took this pendulum to swing back and forth. Well, period is equal to 2 pi divided by omega, isn't that straight out of our toolbox? And so 2 pi divided by omega is 2 pi times the square root of L over G. And there it is, the period of a simple pendulum. Simple meaning a mass on the end of a string. What does the period of a pendulum depend on? The planet we're on, because little g changes depending on where you are, right, with respect to a planet's surface. And what's the other thing? The length. The length as measured from the point of articulation, wherever it's hanging from, okay? So whatever length we have, right, okay, we measure from that point to the center of mass of the mass that's on the end, right? And if I make this length longer, what happens to the time it takes for it to wiggle back and forth? It increases. Does the amplitude matter? What's amplitude for the pendulum? It's kind of how far we get from this hanging position, right? So does the amplitude matter? Yes. What was the assumption we made to make the math easy? Small angle approximation, right? This result holds as long as we don't go more than 5 degrees, right? From the, if we go, wah! Right, now we're in the big differential equation territory, okay? But even then, in the big differential equation territory, even though there's some result, there is a little bit of connection between amplitude and length. It's not nearly as strong as, say, the mass and which planet you're on and some other factors that figure in there. Okay? So now that we've got that, all the other, so frequency, how do you find the frequency of a pendulum? It's 1 over whatever that number is, right? Okay? How do you find its amplitude? How do you find its maximum speed? How do you find its maximum acceleration? It's just, it's all there in total. Because you have omega, right? And you're done. So that's the power of this toolbox. Oftentimes in physics, what we'll do is not reinvent the toolbox. What we'll do is we'll try to get something, even though it doesn't look like a spring, right? We'll try to get something to look like a spring. We'll play these math games where it's not so much doing math as it is finding a way for it to match the differential equation that has already been solved by people that are much smarter come before us, right? So, and again, I've watched engineers and physicists take things that don't even remotely look like spring. Oh, well, let's drop a watermelon off the edge of the building, and okay, let's figure out what happens when it hits the ground. Well, for a quarter of a period, it's kind of a spring. They don't bounce so much as anyway, right? So again, it's a quick go-to, and if you want to do the thing for realsies, well, now you've got a career on your hands. But if you want to be able to solve problems really quick, this is a way to do it. Okay, so why would any of this, what sort of practical application does any of this stuff have? Because I know we've been doing a lot of sort of like kind of heavy physics, conceptual physics. Most of you are engineers. We got to ground this in something. Okay, so finding the period of a pendulum. Well, this was a big problem back in the 1700s. Okay, because this was how you told time, right? A second was a certain length of a pendulum, blah, 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 blah. And when you got on a boat and you had to navigate somewhere and the boat's moving around, what happens to your pendulum swing? Okay? And so they had to figure out ways to make clocks that could function independent of a boat's motion, because knowing what time it is told you what your longitude was. Longitude was east to west around the planet. Latitude was easy. You go look at the stars, you can figure out where you are. But longitude was a much harder problem to solve, and it came down to figuring out how to make things that have springs in them but are not affected by the motion of everything else around them. As we get into the modern age, we don't have pendulum clocks anymore, right? We don't even really have quartz clocks anymore. But we have our atomic clocks that tell our phones what time it is several times a second. Okay? So you're like, so what's the big deal? Well, knowing the period of a pendulum becomes critical when you start thinking about physiology and how the human body functions. Because as you walk, your body has a natural period and frequency to the way that you walk. Okay? Where's the pendulum in your body? It's your legs, right? Okay? You've got these big pendulums, right, that are swinging back and forth. Now, does this look, be careful, does this look like a simple pendulum where all the mass is like at the end of the, no, it doesn't look anything like that, right? Okay? It's got mass all the way down, right? And so, I'm not going to show you all the ways of doing it, but you can do the analysis that we did. You can do something very similar to this. Only instead of assuming all your mass is at the end, you think of your mass being spread out. So you reach back into the physics 4A toolbox where there was moment of inertia. Some of you are in panic, right? Okay. Moment of inertia was a description of sort of mass in rotation. How hard is it to get something to rotate? And you can pull off, right? We call this physical pendulum, okay, a simple physical pendulum. The period ends up being 2 pi. 2 pi is everywhere. Why is 2 pi in here? Circles. right? This is all circles. Circles all the way down. Square root of the moment of inertia divided by mg times little d, where little d is the distance to the center of mass from the articulation point. So the pattern kind of remains. I mean, omega is different for a physical pendulum than a simple pendulum than a spring. But once you find out what omega is, you can very easily solve these problems. Now, in truth, okay, your leg isn't a single physical pendulum. Okay? It's a double pendulum. It's got two articulation points in it. Double pendulum are amazing. They get into all kinds of chaotic behaviors if you simulate them and do all kinds of stuff with them and allow them to go whichever direction. But the math gets more complicated, but it becomes more fulfilling, especially for those who have prostheses. Growing up, I had a friend who had a prosthetic leg. Okay, if I remember correctly, he had a knee, okay, but what he didn't have was the lower part of his leg, right? And so growing up, right, he would walk, well, he'd walk funny, right? If you've seen anybody that's either had a foot problem or leg problem or prosthetic, they tend to have this sort of rolling motion to the way that they walk. There's a word to describe how somebody walks. Anybody know it? Yeah, it's English class today. Okay, gait, not the thing you opened in a fence, but spell that one. I'm not responsible for English. Okay, and your normal gait, right, the way that you walk is determined by like the length of your legs and where your center of mass is, and maybe how stiff your legs are after running yesterday because you haven't run for like 4 weeks. You take that surgery, right? But you have this natural way, okay, of walking. When that natural period and frequency and oscillation get interrupted, you start having this sort of kind of rolling motion. And he would do that, right? Because one half of his body, the physical pendulum, was doing one period, and the other half of his body was doing a different period. Okay? And so one day in like high school, after we had, sort of kind of grown up and were more of our adult size, he came to school, right? And we're watching him walk across the quad, and he's doing that. Right? Absolutely no roll whatsoever. We run over to him, like, hey, man, what's going on, right? And he pulled up his pant leg, right? And he had a new prosthetic. Well, prior to that, because he was still growing, they were kind of giving him these generic prosthetics, right? Just kind of, it's not one size fits all, but it really wasn't tuned to him. But since he had sort of his adult growth on him and they weren't anticipating too much, more changes to his leg size and that kind of stuff, he had a custom-made prosthetic. And I found out later, as I got into physics and I was thinking about this, investigated a little bit, that's what they do. They model the prosthetic after the limb that has the normal period. And they change its weight and its features and all that kind of stuff to be able to match the periods between the legs, and the quality of life for the individual goes through the roof. Right? So he lives a life now where the only way you know that he has a prosthetic limb is if he takes it off and hits you with it. Right? So we always used to, new kids would come to school and we're like, hey, you go kick him in the leg. Right? The kid would be like, really? Yeah, walk up to him, ask him if he can kick you in the leg, right? Yeah. Really? Hey, can I kick you? He's like, yeah, this one. Go ahead. Okay. And then we'd psych people out. He'd be sitting there like this or something, and you're like, hey, do it. And he'd take like a fork and go, bam! Right into his leg, and all people didn't know it was going, ah! We had a lot of fun. But anyway, young Mr. Balogh was a force to be reckoned with, that's all I'm going to say. The Boston Marathon and the bombing that took place, okay? There were many stories that came out of that tragedy. One of them stuck in my mind, though, because, well, it had physics in it. One of the runners who lost her foot was a member of the Boston Ballet, very prominent member of the Boston Ballet. And the doctors told her that you're not going to dance at that level anymore, right? Your prosthetic is simply not going to let you be on point or any of that kind of stuff. I can't even imagine how devastating, right? Losing your career like that could be. And the engineering students in MIT caught wind of this story and said, no, that's not good enough. And so they went to the robotics lab and they designed a prosthetic, right, that had batteries and actuators and servos in it that so well matched her natural ability that she was able to dance again in the Boston Ballet. Like, we are living in Star Trek, right? Like, and that research, that project that went from sort of this driven by sort of the human story, right, became this engineering thing where we're not going to let the bad guys win, to now they're starting to design prosthetics with the technology that the MIT students are trying to. It is a great time to be alive. I know you guys hear all the time how bad the world is, okay? But it really is an amazing time to be alive. We've got a lot of problems, we're going to fix them. We just need to stop paying attention to people who are, oh, we can't fix anything. Well, you know what, leave. Right? Because we got some work to do. All right. Making this a little bit harder. Because everybody loves making it a little bit harder, right? No. You make it harder because it's more interesting. Okay? Why is this not? Here we go. We have done everything so far without any friction. Now we're going to add some friction. In simple harmonic motions, and we're going to do this conceptually, right? We're not going to do very much math at all here, okay? When you add friction, we call it damped oscillations, okay? The dampen oscillation is to suppress it, to remove its energy, okay, while it is doing its oscillation. I have a picture up here on the screen of an automobile or motorcycle's shock absorber, okay? The spring, okay, is part of the suspension system of the vehicle. And when you're driving your car, this system of springs that's in your car is responsible for making sure that when there's a bump in the road, right, and your tire is going to go into that bump or over that bump or something, that the rest of the car doesn't do the same thing. Right? If you've ever ridden in like a wagon or anything that doesn't have a suspension, you know how uncomfortable that ride can be, right? So the suspension is there to take the bumps out. Well, if we just put springs in things, what would your experience be driving down the road? Drive, hit a bump. Boom, 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 right? Okay? All the way down the road. There'd just be this, right? Bouncing up and down. And so what they do is inside the spring, they'll put in this shock absorber. Usually they just call it shocks, right? The shock absorber's job is to do what? Absorb shocks. Very good. In the language of physics, we say it's going to damp the oscillation. It's going to, yes, the spring wants to bounce up and down, but we're going to stop that spring from bouncing up and down. But we're not going to do it sort of like abruptly, right? If you've got a lot of dampening in your system and you hit that bump, what happens? It's like a severe, I need kidneys, right? Okay? But if you don't put enough shock absorbing or dampening in, your system will oscillate a lot. So there's sort of three grand regimes, okay, for damped oscillations. And we'll just sort of plot them here, okay? And this is like an amplitude per time sort of graph, right? And what I described, okay, those two sort of extremes where you got a lot of dampening and a little bit. We're not going to talk really about the too much. The too much version, I'm going to draw it and then I'm going to erase it. Basically looks like this. right? There's no wiggle whatsoever. It's just a kunk, okay? The underdamped case, the case where the shock absorbing and the dampening is there, the amplitude will eventually go away, but it's still going to wiggle. The underdamped case might look something like this, and I'll just start them all at their peak, okay? So the underdamped case has wiggles in it, right? It is doing the oscillation. It's just as time goes on, the amplitude of that oscillation is falling off. Then you have, there's a case where you can actually get to so much dampening that it actually takes a really long time for the oscillator to do anything. This is called the overdamped case. So this is underdamped. Okay. Overdamped looks a little bit like sort of like that. Okay. And you're looking at that going, well, Mr. Baylor, that doesn't look like a sine or cosine at all. Well, yes and no. It just depends on how many sine or cosine functions you're using. Okay. Anyway, that's getting too much into the weeds. The point is, this would be like if you took a mass on a spring, and instead of letting it bounce up and down in the air, you put it in like a jar of honey. Right? You pull it down, you let go, and what does that kind of mass in honey do? So is it January or July? It just kind of like comes like, right? It's just, there's so much damage. The spring can pull it through, but give up. Right? That's the overdamped case. And then there's something called the critically damped case. This is sort of a Goldilocks sort of situation. But in the critical damped case, what happens is you can get a little bit of a wiggle, but really you kind of come back. And I didn't really draw that right. It can be sort of like this. Okay, you're wiggling. Okay, you're starting the process of the harmonic motion, but then you're going to bring it to a stop within a period of time that is acceptable for your system. So let's go back and talk about cars and car safety and car comfort. Of these three cases right here that I failed to write down the numbers for, the words for, the blue overdamped. Of these three cases right here, okay, we can talk about car safety or we can talk about car comfort. Well, we've got to talk about both. Let's do this. Make that go away. Okay, so let's do a quiz, right? We'll let you think about this on your own and then do it by yourself. Unpause. Okay, so now what we need to do is we need to do not the opposite of, but because you can have friction in a system, right? You can have a simple harmonic oscillator with no friction. That's mostly what I'm going to ask you to focus on. And then we've got this sort of damped harmonic oscillator. We've got these concepts, these three concepts of over, under, and critically damped. But we can also do one better. We can drive our harmonic system with a forced input of energy. So rather than just grabbing the spring and letting it go, I can get it started in the motion, and then every once in a while I can give it a tap, right? And that periodic tap of adding energy to the system is called a forced oscillation. I'm sorry it's being cut off there at the top. In the case of a pendulum, okay, it can be swinging back and forth, but I can every once in a while give it a push. And what happens when I give the push at the right time? The amplitude increases, right? Okay. Well, where have you done this before? It's time to talk about swings at the park. Okay? And so you go out, you look, you do the royalty-free internet sites, whatever, right? Give me a picture of a kid on a swing, right? Okay? And you get things like this. I did look for diversity in these pictures, unfortunately. Found for the free ones, I'm sorry. Right? But come on! I mean, that. Why can't we be like this now? Well, okay, so we can't. Homework. Go find a park, sit on a swing for 5 minutes. Just swing back and forth for 5 minutes. Your day will be markedly improved. Like, I'm convinced every day that you can find a balloon, you're just going to be happier, right? So, go plug it, right? But, I mean, come on. And then there were more.
Oh my
right? Okay. So yeah, we're you tried at some point, right, to get the full 360. And this being the internet, that dog is having fun. I don't know if you can tell from his face. Right, okay. Anyway, the swings. How do you know when to input energy into the system?
Can you slow down?
You're starting to slow. Oh, that point, right?
You get to that point.
Okay, but there's another point where that's happening, right? In the swinging motion, right? As you go back and forth, there's 2 points where that happens. But you don't go woo ha, right? Or if you're the adult, okay, and the kid's on the swing, right? And you're giving the kid a push, right? You don't like push them and then run over here, right? But so the answer is that in order to increase the amplitude of the oscillation, we want to force the oscillation at the frequency that the oscillator wants to oscillate at. So the swing has a natural frequency, back and forth, right? And so you push the child as they're swinging back, you add the energy. And then they do their full period, and then you add the energy. And then you add the energy. Do this as part of your homework when you go out to have your emotional catharsis on the swing. Get on the swing, do the swing, you know how to swing, right? Okay? And then, once you're swinging, maybe not at full amplitude, but like somewhere in the middle, start pumping at random times. Like, you're supposed to pump, right, when you're back here, but try it like at the bottom. Be careful, but try it at the top, okay? And just see what happens, right? When you add energy at the wrong time, the amplitude dies off. It's only when you add energy at the correct time that the amplitude will increase. This phenomenon, where the amplitude of an oscillation increases when you are forcing it, is called resonance. Resonance is the increase in amplitude of an oscillating system when it is driven at its natural frequency. For the swings, that natural frequency, right, is pretty easy to tell. And I love watching kids learning how to swing on the swings, right? Okay? Little kid, right? And then, right? And they're like swinging their legs and they're pulling their arms and they get frustrated because they don't understand why it's not going, right? And then you can just watch the little physicists happen. Right? They'll be swinging, right? And then they'll start screaming at their mom or dad, don't push it, right? Because they figured it out. They've done the differential equations, they know. Right? That they need to, what's the motion? It's really interesting. Usually it's a lean back, right? And your legs do what? Straight out. What have you just done? You've changed the center of mass location of the system. Okay? And then there is this pull on the chains of the ropes and a coordinated changing of the center of mass location of the system. So there's this add of energy from the arms. There's this shift in the center of mass of the system that gives the push. Remember, no object can exert a force on itself and have any kind of net acceleration. But in pulling on the chains, right, which are connected to the structure, that's two objects right there. So there's that force input, there's a shift in the center of mass, which adds an additional torque to the system. It's really cool. Really just a big thing. I just love it. All right. Resonance. Resonance is a great thing on the swings. It's a bad thing in buildings. What do you not want a building to do? Vibrate. Right? Oscillate in any way, shape, or form. Okay? But you've seen what happens when the train goes down the tracks to the thing, to the screen projector. Have you ever noticed? It's a, right? That mount in that ceiling has a frequency that's close to the frequency that that train is emitting through the ground. And I can tell because it begins to vibrate when the train is going past, right? We are matching natural frequencies between the train rolling down the track and the mount in this building. So as an engineer, if you're designing a building and it's in earthquake country, what do you want to make sure your building's frequency isn't? The same frequency as earthquake waves, okay? And so high-rise buildings are nowadays built with suspension systems. Like the foundation of the building is not connected to the earth. There is a foundation, but then they put in spring, really big springs, right? Dampening things so that the building doesn't oscillate while the rest of the ground goes places. What do you not want an airplane to do? Fall out of the sky. Like basic design principle of airplanes, right? Okay. There was an airplane, a passenger plane that was being developed. It's called the Constellation or something. Anyway, I don't remember what it was called because it never made it. What happened was 2 test pilots died on the maiden voyage of this plane. And for the longest time, they could not figure out what had gone wrong. The plane literally had disintegrated in the sky. And it wasn't going very fast, it wasn't going too slow, it simply fell apart at normal speed and all that stuff. And so they investigated, and finally, one of the test pilots on the investigation team was like, I think what we just need to do is we need to fly it again. Like, we don't know what's going on here, I'll do it, okay? And so he took it up with his co-pilot, and I hope they brought parachutes with them. And they were flying along, takeoff, everything was fine, landing gear was working, all this kind of stuff. And they put the throttles for the plane into the cruise power setting, like normal operation setting. And all of a sudden, the co-pilot said, look out the window. And the pilot turned around and looked out the window back at the wing, and the wings were doing this. Okay? And so the pilot instinctively threw the throttle back into idle, and the wings went still. And then he inched the throttle up, everything was fine, everything was fine, got to the cruise setting, and the wings started. This is not how airplanes work, okay? Right? What they discovered was the engines, they were propeller-driven engines at the time, the natural frequency of the rotation of those propellers and the engine itself was matching the resonant frequency of the wings. And so as the system got driven at the frequency, the amplitude, and what happened to the first crew is that the plane literally tore itself apart, right? The wings were flapping up and down in a way that we humans don't fly by flapping our wings, right? We fly by going fast. So, yeah, you gotta watch out for resonance. This was from the 1940s. No CGI.
Perhaps, among other things, the Tacoma Narrows Bridge was the most spectacular aeolian harp in history. Unfortunately, its first performance was destined to run only about 4 months. In the meantime, she was a beautiful bridge. beautiful but a little strange. Even before construction was completed, people observed its peculiar behavior. That was because, even in a light breeze, ripples ran along the bridge. After a while, one of the local humorists called her Galloping Gertie. And for fairly obvious reasons, the name stuck, at least until the 7th of November, 1940. Then as now, Seattle and Tacoma were sports-minded cities. For 4 months, a regional sport was to drive across the bridge on a windy day. While some claimed it was like riding a roller coaster, others found it a little disconcerting to see the car in front disappear. How popular this bridge sport was, or to what extent it might have spread across the country, is anybody's guess. On November 7, 1940, the winds were relatively moderate, about 40 miles per hour. A new mode appeared. Rather than ripple, the bridge began to twist. A wind of 40 miles per hour is not too strong, but it was strong enough to start the bridge twisting violently. And at 11 a.m., it fell. Investigators were mystified. A bridge constructed according to the best engineering standards of the day, perhaps the best bridge in the world. This was not a bridge that was supposed to collapse. What in the world?
All right. Now, to say that resonance was at fault here is a gross overstatement and a travesty of science. Okay? There's a lot of very complicated things that are happening here, not the least of which is something called vortex shedding. But let me simplify, okay? With the acknowledgement that I'm about to make bridge designers and engineers very angry, okay? Did you catch what the wind speed was? 40 miles an hour. The Tacoma Narrows routinely sees hurricane force winds blowing in the channel. Okay, it's two kind of hills on either side, and it's coming right down the Puget Sound, right? Okay, and as you funnel the wind into a narrow space, okay, it speeds up. So 75, 85, 95, 100 mile an hour winds were not uncommon in the area. Like the bridge designers knew they had to design this bridge for 100 miles an hour, and so they did. Right? It was going to withstand anything that Mother Nature could throw at it. But at 40 miles an hour, consistent 40 miles an hour wind, we got a torsional oscillation. You see, Joseph's kind of a line down the center of the bridge, and it was the sides that were going up and down. Aerodynamically, what was happening is as air rushed across the surface of the bridge, when it hit the back trailing edge, the air has to separate from the surface that it's blowing against, and as it separates, it kind of kicks in a circle, and it develops this thing called a vortex. It's like a spinning circular motion within a fluid, and as that vortex forms and then peels off, okay, separates from the surface of the bridge, it gives a little push. And so there were vortices forming on the top and bottom surfaces of the bridge, and the rate at which they were peeling off and giving little tiny pushes to the bridge at 40 miles an hour exactly matched the torsional resonance frequency of the bridge. And so what were very tiny little pushes by turbulence in the air got magnified at resonance. And eventually, it doesn't matter how good your reinforced steel and concrete is. That was steel and concrete going through about a 12-meter amplitude on either side. So we're talking about this thing is going almost 50 feet, right? Up and down. After the Tacoma Narrows Bridge, every single bridge that has ever been designed has not only been designed to withstand winds, but has also been put in a wind tunnel. Like a scale model has been developed, put in a wind tunnel, and they now test the aerodynamics of all the structures. So civil engineers couldn't just design against earth, now they have to design against wind. There's a building in Shanghai, China, that's got a big opening in it. Okay? They had to make sure that they weren't causing lift on parts of that opening. So they did. They designed baffles in it so that any wind trying to blow through it gets sort of broken up. Anyway, so just an amazing amount of physics that goes into a lot of different design processes. So what we've done is given a foundation, right? Simple harmonic motion is the rule. It's the one that we're really going to keep you, right, focused on. Yes, you do need to know about damped motion and driven motion, but conceptually, no math. Maybe I gave you one homework problem. The book has the equation for like omega for a damped oscillator. It's kind of big and ugly, but you just plug things in. I don't remember if I gave you one or not. Did I? Did I give any homework with damped or forced oscillations in it? Okay. Good. So the real sort of meat, okay, of this first unit is waves. What we want to do is we want to take everything we've learned about simple harmonic oscillators and apply it to this concept and idea of a wave. Because really, physics 4C is wave mechanics. So much of what we do in physics, except thermodynamics, because thermodynamics is dumb, right? We're going to do it. So let me ask you a question. What's a wave? Got length? People struggle when I ask that question. Like, I don't know, Mr. Beck. Tell me what things are waves. Like, give me examples of waves.
Sound.
Sound waves? Water.
Light.
Light. What? Radiation.
Gravity.
Ooh, gravity waves nowadays. We'll get to there in the end. Okay, when we talk about cosmology. So you can give me examples of waves, but telling me what a wave is becomes a little bit more tricky. And I think this is actually one of the few times in physics where you come and there's like absolutely no previous experience with the, like you've had experience with waves, but like definitionally, I don't think anybody's probably ever taught you what a wave is. So I want to teach you today, and I want to teach you in a way that makes you part of the wave. You ever seen a wave in a stadium?
Yeah.
Okay, we're going to do something similar, only we're going to do it a lot better. So what I need you to do is I need you to stand up. Stand up. And what I need you to do is form a big horseshoe in this room. I want it to kind of start here. I want it to go all the way around the back, and come back up here to the front. And I need you standing shoulder to shoulder with each other. Sorry, got to break the social distancing rules here. Okay, no gaps. So shift as we need, but we need everybody standing shoulder to shoulder. Yes, so scoot that way. Scoot that way.
He's gonna like go.
Okay. Yeah, no, I'm not going to shock you. Okay, so you kind of close shoulder to shoulder. Okay, right? So what we're going to do, okay, is I am going to form different kinds of waves. But I want to test your wave-making ability to begin with, okay? So in a stadium, right, when you're doing the wave, right, you sort of stand up and throw your hands in the air and cheer and all that kind of stuff, okay? So you can cheer if you'd like, okay? It's totally up to you, right? But what we're going to do is we're going to do just wave your hands in the air, right? And I'm going to start it at this end. You good? Okay, we'll find out. Right? We're going to start at this end, right? I want to see the wave propagate all the way to this end. Are you ready? So without teaching you anymore, let's just see how good you are at this. Ready? Get your right on it. 1, 2, 3, go. Okay, I've seen more energetic waves. But that was pretty good. That was pretty good, okay? So, analyze your motion, okay? This was you. You ready? Okay. Analyze your motion, but we're going to do the wave for real this time. And as a gauntlet, I'm throwing down a challenge to you. I'm telling you, third graders nail this. Okay? Adults, what I'm going to do, okay, Justin, you got the easy job. Okay? You just look at me. Okay? And I'm going to start a wave, and as it goes, I'm going to start another one behind it. Okay? Now, you guys over here, can you be watching what they're doing? No, because there's still something propagating down your direction, right? Okay? So, I'm going to send wave after wave after wave, right? Through my wave medium here. You guys look great. Best looking wave medium ever. You ready? Here we go. Go. Oh, you guys are pretty good. Oh, you passed third grade. I can tell. Oh, don't lose it. Don't laugh. You can do it. You can do it. Oh, you guys are making each other out. It's fantastic. Very good. Usually, after like the second pulse, everybody does it. Right? Okay, so what was your motion? What is this? Not a standing wave. Not there yet.
Spring.
It's a mass on a spring. It's an oscillator, right? You were doing this. Now, you had to do it at the right time, right? Because if everybody's doing it right at the same time, that's not a wave. So what's a wave? It's a series of connected simple harmonic oscillators. This is why we don't teach the definition when you're young. Because that didn't help. It's probably not helping now. But let's see if we can get it to stick. Right? Your motion is that of up and down, but you have to do it when the parts of the medium near you, right, are doing it. So that something, energy, a disturbance, propagates, right, through the medium. You have to have a medium. Now, the speed that that thing propagates through the medium depends entirely on the medium. So, I now want you to try to do this wave as fast as possible. This is going to be a single pulse, okay? But I want you to do it as fast as possible. Are you ready? I want to see the pulse get from here to there as fast as you can. You ready? Go. Okay, that's pretty good. Okay? Now, I'm going to change the properties of the medium. You are not allowed to do your up and down until the person next to you has finished theirs. Does that make sense? Everybody gets a solo. Go. Keep going. Okay, good. Good. Okay. How would you describe the speed of this wave pulse compared to the last one? Terrible. Slower, right? Okay. Good. Oh, everybody looks so good. Okay. Changing the properties of the medium. Change the speed at which the wave propagated through the medium. So the speed of a wave depends on the medium, the material that the wave is in. Okay, and that it's traveling through. It really doesn't depend on anything else. I'm being very strong here because you're about to forget this. Okay, watch it happen. Okay, now we're going to change one more thing. We've been doing this kind of wave. It's called transverse wave. Don't wait. And we're going to go over all this again and get a chance to write it down. Okay? This is a transverse wave. Transverse because the direction of oscillation was perpendicular to the direction that the wave traveled. So this time what I want you to do, you're going to have to touch each other, I'm sorry. And if you don't like that, you're going to have to just step out, which is fine. Okay? What I want you to do is put your left arm on the right shoulder of the person next to you. Be nice.
Left arm on the right.
This side, okay? On this side, okay? Okay, good. It looks like we figured it out eventually. All right, okay? So now, very gently, okay? When you get pushed, you're going to push the person next to you. Understand? Okay? What I do not want to see is an increase in amplitude in the guy. Okay? So, go. Gentle. Gentle. Look, gentle. Okay, good. You can stop touching each other now. All right. What was your motion now? It was parallel, right, to the direction that the wave went. Okay? The pulse, it's really not a wave because a wave is a continuous stream of things, right? It's really a pulse, right? So the pulse direction was traveling longitudinally through the medium, and you were also. So we call that a longitudinal wave compared to a transverse wave. All right, go ahead and sit down. And let's review everything that we just learned. Okay. And what I'm going to do is I'm going to simulate a wave, right? Okay. So this is a mathematical simulation, but it really closely resembles what's going on. Okay. So we have a medium, right? In this case, I've got these little tiny marbles, whatever. They're all connected to each other like a string, okay? And they've broken it up into little tiny marbles so that we can see the individual elements, right? But like a wave on a string, a sound wave, it's more or less continuous, right? I mean, we can break it down to the individual atoms, but a string is a string. Okay. So what I'm going to do, it's got frequency, it's got amplitude. I've taken all the dampening out, okay? And we've got a tension to it. I'm just going to hit play here, okay? And we're going to watch this wave happen. Now, the advantage of the simulation is that we can slow down time. This is very slowed down, right? So we can see what's going on in this wave. So, first of all, how would you describe this wave? Transverse or longitudinal? This is a transverse wave. And what's the definition there?
It's perpendicular.
The wiggle, okay, the way that the individual things are going, is up and down, which is perpendicular to the direction that the wave happens to be traveling. Okay? And what's the other word you use when it's parallel? It's a longitudinal wave. Okay? We are going to use transverse waves in this chapter, and then we're going to switch to longitudinal waves in the next chapter. The next chapter is all about sound and sound propagation. Sound is a longitudinal wave. Transverse waves. So the big difference there is that fluids, they can't do transverse waves. I know all of you just started thinking about the ocean. That's different. Okay? That's the interface between a fluid and a gas. So weird things happen in interfaces. We're actually not going to talk about water waves. Okay? But in general, if you've got a fluid, which is a liquid or a gas, it's going to be a longitudinal wave. Okay? If it's a string or anything, right, a drum head, any of that kind of stuff, it's going to be a transverse wave. Okay. So, what direction is this wave traveling? Looks like it's moving to the right. And how did you determine that? We follow a peak of the wave, right? We can see that that peak moves. How would you describe the amplitude of this wave? How would you measure it? Well, there is a middle, right, an equilibrium right here. Okay? So what would the amplitude be? The distance from that point to like the maximum peak. What's the other thing, the dip?
Trolley.
I am not responsible for the English spelling of this word.
True.
I'm sorry. Like, if you've been learning English, I apologize for my broken language, right? The English is this language of, well, here's the rules, and then you break all of them, right? I before E, except after C. If I knew that that was a lie in high school, I'm mad. Anyway, this is pronounced true. Okay? Or trough, or truga. The word trough should be spelled like that.
Yeah.
Okay? Or some variant of that, right? Okay? Anyway, right? But that word, trough, right, is the opposite of a peak. You have peaks and troughs. Sometimes peaks and valleys. I see that one more often being used in sort of modern, like high school physics textbooks. Okay, peaks and valleys, which is not bad, but whatever. So we got peaks, we got troughs, we got an amplitude. Does this thing have frequency?
Yes.
Does it have period? Okay, the new thing that it has is speed. Let's pause the simulation for just a second. Right there. Okay? I'm going to take a snapshot. So part of the difficulty of learning about waves and studying them is you really can't do this on a paper or even like an iPad's notes screen, right? You can always sort of link to the simulation and run it on the web, but like analyzing it, right? We're really just sort of taking snapshots in time. When I come up here and I go, oh, this wave's propagating, and I go, oh, hey, it's a sine wave, right? Really what I've done is just I've looked at it at an instant in time. What do you have to do in your brain when you see this? You got to look at it moving, right? Moving left or right or whatever. We'll get into all of that, right? But let's sort of get the basics down visually in this snapshot that we have here. So we talked about the amplitude, right? So the amplitude is from equilibrium to peak, but it's also equilibrium to trough. Those should be equal to each other. A new term that we will define is the peak to peak distance, or, and I very cleverly didn't do it right, the trough to trough distance. Those two things should be exactly equal. This distance in units of meters, because it's a distance, is called the wavelength. And the symbol there is the Greek letter lambda. Lambda, to draw lambda, okay, what you do is you draw a candy cane, okay? So this candy cane though, okay, this candy cane had a little bit too much Christmas party, okay? It's kind of staggering around on its way home, and it's falling over. And so what it does is it sticks out its legs so it doesn't fall over. Okay? So it's supposed to be sort of like a, kind of more like, I don't know, fancier type thing. You'll see it in books. But for the shorthand version, you just kind of do the, it's like almost like you make a 2. It's like writing the number 2, right? But you go like that, and then you lift up your pencil and then bring it down. Right? So that's the symbol, Greek letter lambda, L-A-M-B-D-A, because apparently the Greeks couldn't spell either. Okay? And it is a length. So we got amplitude, we've got wavelength. That's a new thing for waves, right? Let's get back to the animation. Okay. I want you to look right at this green ball. Do you see it?
No, staring at it.
What's it doing? It's a simple harmonic oscillator, right? And so this simulation shows you how it's a collection of simple harmonic oscillators. Are they all in exactly the same position at the same time? No. Do they all have the same frequency? Yes. Do they all have the same period? Yes. Do they all have the same amplitude? Yes. But it's in the differences of when they are at amplitude, or when they're at equilibrium, or whatever, right? that we get this phenomenon of the wave. So we've got to take from our simple harmonic oscillator sort of toolbox and our ideas and extend it out in space and time and give you a new space-time equation that describes what's going on here. But before I get there, I'm going to show you what happens, okay, when you change things. Remember I told you that the properties of the medium is what determines the speed of the wave? So what I want to do is I want to change the frequency, okay? So we kind of have to get it, it's a little bit hard to do this, but this thing is moving across the screen at about this speed, right? So what did that take? 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, about 5 seconds, right? Okay? Now I'm going to change the frequency. I'm going to increase the frequency. Okay? Notice what changed? Wavelength changed. The distance between peaks got shorter, didn't it? Okay? Frequency is now bigger, right? These things are bouncing up and down faster than they were before. What about the wave speed? Faster or slower? The same. I told you before and I told you forget it. The properties of the medium, right? I changed the frequency, I didn't change the properties of the medium. Okay? So, to prove it, let's see. We got to get one here, right? 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,005. Right? That peak is moving. It looks faster, doesn't it? But that's like an optical illusion. Your brain's going, well, they're going up and down faster. No. Okay? The speed of a wave depends on the medium in which it is traveling. Nothing else. If the properties of the medium change, then the wave speed changes. Let me get this frequency back down to a little bit. Okay. I got to give it a full 5 seconds for it to sort itself out. Okay. Now I am going to change the properties of the medium. I'm going to change the tension in this string. Okay. And I'm going to drop it down. Okay. Simulation does break a little bit because it changed the speed of that, right? It's cheating a little bit. But these are now moving across much more slowly, aren't they? Okay, right? And because of the nature of the simulation, there isn't enough particles to kind of see what's going on here, right? But by changing, and again, that's cheating. It shouldn't be going that fast, right? Okay, right? But by changing the properties of the medium, I change the speed at which it propagates. Okay, so let's get off of this. Back to this, okay? Let's start developing a mathematical toolbox, okay, for waves and wave motion. And I'm going to drop, now I'm not going to prove anything to you. I'm just going to tell you that these are the functions that do blah, 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 and then we'll sort of circle back and I'll show you where they come from later. There is a key equation that is used over and over and over again, not just in this unit, but in all the units except thermodynamics is thermodynamics. You're going to see it. I'm going to refer to this. We're going to refer to it in optics. We're going to refer to it in quantum mechanics. We're going to refer to it in relativity. We're like, it's everywhere. The speed of a wave. And this equation trips students up constantly. What's wrong with that, Mr. Gaylor? It's like easy, right? The speed is equal to the wavelength times the frequency. What's wrong? If I double the frequency of the wave, what happens to the speed? Nothing. What did your mathematical brain want to tell you? It doubles the speed. No. This equation is a trap. It's a trap. It's a trap because it's a relationship between wavelength and frequency. What happens when you double the frequency of a wave? the wavelength gets cut in half. And you saw that. I increased the frequency and the distance between the peaks got shorter. Okay? What happens if I cut the frequency by 4, divided the frequency by 4? The wavelength gets 4 times longer. So what this equation is the physics of the inverse relationship between wavelength and frequency. It is not the velocity depends on the wavelength, but the velocity depends on the frequency. What does the velocity of a wave depend on? Medium. Properties of the medium in which it is traveling. If you can cement that in your brain, that the speed of a wave depends on the properties of the medium and nothing else, you will save yourself quite a few tears. Okay? And the books and the homeworks will try to trick you. Right? So be aware of it. Okay, tension, say in a string, right? If you got a wave on a string, that's changing the properties of the medium. For air, if we change the temperature, which alters the density, if we change the pressure, like any of those properties of the medium, then the wave speed is going to change. But don't get trapped into thinking that if I change the frequency, I change the speed. No. If you change the frequency, you change the wavelength. Okay. Wavelengths units are what? Wavelength. Meters. And units of frequency are?
Hertz.
Hertz. And what's a hertz?
Per second.
It's a 1 over a second. So what is the speed of a wave's units?
Meters per second.
Right? Okay. We also are going to bring over omega, which is 2 pi divided by the period. Again, the period is inverse of the frequency. That's still, again, this all comes over, right? And, well, I shouldn't have boxed that one yet, is equal to 2 pi f. So again, these are recycled because it's all simple harmonic oscillators connected together. We are going to, so omega is omega. It's an angular frequency, okay? Radians per second instead of just 1 over seconds. We're going to introduce a new constant. And I would like to apologize in advance for the symbol of this new constant. It's not my fault. I didn't do this, okay? But the symbol is K.
Oh.
This is, yes. There are what, 26 letters in the alphabet? And I have always been a proponent that we should just start adopting Chinese characters or something, right? Hieroglyphs, emojis. Something else, okay? Besides the 26 letters of the Latin alphabet and the 25 of the Greek alphabet, or how many? 26? 25? I don't remember. There's not enough symbols. Like seriously, just use emojis. This K, called the wave number, is 2 pi over the wavelength. How can you possibly know what K you are dealing with? Is it a spring constant? Or is it a wave number? Or if you're in physics 4b, is it 8.99 times 10 to the 9th? Right? K is like everywhere. It's horrible. The way you tell the difference is by context. If there's a spring and you've got a force and a distance, that's got to be spring constant K, right? But if there's a wave around, chances are the K that you're dealing with is the wave number. Okay. So again, I apologize. It's not my fault. But I suppose I'm guilty because I propagate the symbology. But I do want you to be able to talk to other engineers outside of Fresno City College, right? If we ignored the rest of the world, I could make physics so much easier, right? Okay, because this whole have to communicate and work and not get sued. All right, so here's kind of the big change, right? The function that describes this wave mathematically. So in simple harmonic oscillators, we had position as a function of time, velocity as a function of time, acceleration as a function of time. We actually don't really care that much about like how fast one of those things is. We're more concerned with how fast the wave is going, right? So what we got to do now is like instead of a position as a function of time, I need to give you a position as a function of position and time. What? What? We describe waves, okay, on an XY axis. Like I told you, it's a snapshot in time. You notice how time is not on this axis? Okay? So this function, y, as a function of where you are horizontally and what time you're at, this function is going to give you where you are up and down. So if we feed a bunch of positions and a bunch of different times in here, right, we will get the curve, but the time will give it the motion. And since we can't do that on paper, we ignore the time axis, right? But that doesn't change the fact that a wave function is a position and time function. Our simple harmonic oscillator was the position and time. That was it. Now we've already got these three variables that we've got to deal with. And I hope it comes as no surprise that waves have amplitude, that they are described by either cosine or sine functions. Okay? And then there's this, kx minus omega t. Now, your book is going to write this as y of x and t is equal to a cosine of 2 pi over lambda x minus 2 pi ft. Okay, what is your book done? It's made it look worse. Okay? It's one of the few physics textbooks that writes waves like this. Okay? Most physics textbooks will do kx minus omega t. And why are we using k and omega?
Short.
It's just shorter, right? It's just shorter and faster to work in units of k. What are the units of k? What's lambda? Meters. So it's an inverse meter. Okay? Which is weird, but it works really fast. Because you take an inverse meter times a meter, and what do you get? Nothing. And then you take a radian per second times a second, what do you get? A nothing. And so what do you want the arguments of this thing to be? Nothing or radians. Which is nothing. Right? Okay? Because you can't do sine or cosine functions unless it's a radian or a degree. Okay, we don't do degrees, do radians. So that's kind of what's going on here, right? Kx minus omega t, you'll see this on the internet, you'll see it a lot of other places. So I want you to get used to it. Even though your book kind of does it the big ugly, I call that. Okay? It's still the same thing. Okay. This function right here is the function for a wave whose peaks are traveling to the right along the positive x-axis. Okay? Do you want to take a guess as to what the function looks like if it's traveling to the left? I am not responsible for the properties of mathematics in this universe. But in order for the mathematical function in time to propagate from the left to the right or along the positive x-axis, the function must be a difference. You can go to like Wolfram Alpha, plug these in and say simulate this for me and you'll see. Okay? If you got a minus sign, a difference between those two terms, your wave will go along the positive x-axis. If you put a plus sign in, it will go along the negative x-axis. So how do you tell what direction your wave is traveling? Look at the sign. And if it's negative, it's the difference between the two things. Which way is it going?
Right.
along the positive x-axis, which makes this person's dyslexic brain want to scream. Right? Because now nothing is that. Okay? But it is the way it is. Okay? All right. I think I gave you kind of more or less the complete toolbox here. We could get into arguments over sine or cosine, like, but that, again, it devolves into, well, how does your wave start? And the answer is, well, waves don't really start. They just idealize waves in physics. So we'll get boundary conditions on our waves in a bit. Okay? Waves wiggle. And it's an infinite wiggle, right? So it's just a question of, where do you want to be in time? Time 0, you want to be here? Fine, we'll use this one. Right? It's wiggling. But that's all that really makes any difference. I know I've been talking for a while. I am almost done. Let's just quickly do a couple of examples. And these tend to go pretty quick. Again, because you have the toolbox, right? And so it becomes a matter of concept and definition and being able to match terms and all that sort of stuff. Okay? And, man, why does it keep cutting stuff off? Is it going to let me? Okay. It should now be less cut off. I will work later to try to tune it. All right, now we can see it. Okay. So the wave is moving to the right. What do we instantly know? Kx minus omega t. Okay. We've got amplitude, we've got period, we've got wavelength, and they want us to find the function that describes the wave. But we already know what the function is. The function looks like y equals a cosine kx minus omega t. So if we're going to find this function and fill out the details, what do we need to define? We need omega and what's the other thing that's not a variable in here? The wave number, k. So we need k and omega. We have amplitude, don't we?
Yeah.
They just told it. Okay. So how are we going to find the wave number and the omega? Well, omega is equal to 2 pi f, isn't it? So if I take, let's see, 2 pi over t, because they gave me the period, didn't they?
Yeah.
So it's 2 pi over 3 halves, which is 4/3 pi. You can do decimals if you want. Okay. So there's my omega. How am I going to find my k? Oh, did they give me the wavelength? Yep, they did. 2 pi over the wavelength. It's 2 pi over 2.5, which is 5 halves. So that's 4/5 pi. And now away we go, right? So y is equal to 0.6 cosine 4 pi over 5 times x minus 4 pi over 3 times t, right? Yeah. In SI units. So when I write in SI units, what do I mean? The amplitude's in meters. Time is in seconds. Distances are in meters, right? Okay? Everything works together. So make sure you're in units of meters for your wavelengths. Make sure you're in units of meters for your amplitudes. Make sure you're in units of radians per second for your omegas. Inverse meters for your wave numbers. You'll be all right. Okay, does this stretch your brain at all? Okay, so I want you to be able to do it that way, but I also want you to be able to do it the other way. If I give you a function like the one on the screen, what can you tell me right away? Its amplitude is 10 meters. Okay? It's moving to the left. How do you know that? Because it's got a plus sign in it. Right? And can we find speed, wavelength, and frequency? Sure. How do we find the wavelength?
Kind of go back to
What is K? It's 2 pi over 3. How do you know it's 2 pi over 3? It's the thing in front of the x, right? Okay. And so we know that's our wave number. And we know that our wave number is 2 pi divided by the wavelength. So our wavelength has to be 2 pi divided by our wave number. So that's 2 pi over 2 pi over 3, which last time I checked was 3. 3 what? Meters, because we're using SI units. And we're finding a wavelength. Okay, so we found the wavelength. How do we find the frequency? Omega is equal to 2 pi times the frequency, right? So frequency has got to be omega over 2 pi. Omega is pi over 6 all over 2 pi. So the pi's cancel and I get 1/12. Did I do that right? 1/12 hertz. Right? So there's the frequency. And now, how do I find the speed of the wave? It's wavelength times frequency. Right? So the wavelength is 3, the frequency is 1/12, so this wave must be going 1/4 of a meter per second. By the way, one thing you can throw into your toolbox if you'd like, because it's exactly the same thing. V is equal to wavelength over frequency. Well, what's wavelength in terms of wave number? It's 2 pi over k, isn't it? And what is frequency in terms of omega? It's omega over 2 pi. What's V? You've seen that before. We'll talk about the problem that you did on your math preview, the very first problem, tomorrow, when we really talk about the wave equation. And then we'll get into standing waves. Thank you so much, right? The rest of the time is yours. You get your homework done, right? Ask any questions you want. I will be here, and then I repeat the lecture at 11 a.m. I suppose you can say if you want for a repeat. So have a great rest of the day, and feel free, please, to ask me whatever you need.